that we have SI going this week. Shai, did you have SI yesterday? Good. And there'll be some tonight at 4:30. Always a good thing to do. And remember, as I've said in the past, uh, the more that you can study with another person, whether it's a study partner, whether it's with Shai and the other students at SI, or with me, and even a few seconds up here in front with me or out in the hallway with me when I'm getting ready for class is valuable. And it's much more efficient for learning. And learning and thinking is what you want to be able to do in order to prosper in this class. Now, we have a full outline of stuff, and we have a bunch of clicking to do. But before we do that, I want to introduce our new GTA, Graduate Teaching Assistant. Nisha, could you come up, please? This is Nisha Baral, and she's a brand new grad student for the physics department, and she'll be working with us the rest of the way. And she is from the country of Nepal. And Nepal is a place where there are these big mountains, which is, in fact, the biggest mountain of them all. Mount Everest is in Nepal. So we don't have any of those here in Florida. I wish we did. Even a tenth of Mount Everest would be nice. But anyway, so Nisha's from Nepal, and she's going to be working with us. Okay. And she'll be working with us here in this class, and also inside web courses, coaching, and stuff like that. Now, we're trying to get Miss Darien back online as well. So, but due to some bureaucratic mix-ups and stuff at the beginning of the semester, this is what we're going to work with for right now. Just one, and Nisha's a grad student, and so she's a great one to interact with too, because she's an expert on physics. So we got a lot of good experts. Now, last time we were talking about energy and momentum, and this was our summary slide in which we kind of tied it all together. The whole idea of taking a single trajectory, a free fall path, and dividing it up into temporal segments, i.e. stroboscopically, or spatial segments, i.e. with a meter stick, or in this case an 18-meter stick, led to different dynamical quantities being sliced up into equal bite-sized chunks. And for the temporal segment, the equal bite-sized chunks were momentum chunks. For the spatial segmentation of the trajectory, or the spatial partition, it was energy. Side note, and go ahead and jot this down if you didn't get it last time. The unit of energy in the metric system is called the joule. In terms of the fundamental units, it's a kilogram meter squared per second squared. And unlike momentum, it does have a special name. It's named after a British scientist named Joule, who did a lot of thermodynamic energy type experiments. It is also equal to a Newton meter, because what we found last time, the work was really the product of a force and increment to the path. A force parallel to the path, so many newtons parallel to the path, times the length of the increase in distance or the decrease in distance, delta x or delta y, whatever it happened to be. And so 1 unit of energy in the metric system is called a joule. It's equivalent to a kilogram meter squared per second squared. It is also equivalent to a Newton meter. And sometimes a Newton meter, or Nm, is helpful if you're working on a problem and you're trying to get a distance or something like that. Sometimes instead of going to kilogram meter squared per second squared, just going to Newton meters is a little helpful, a little more helpful when you're trying to cancel stuff. So now I want to bring up one last comment to you. So we're going to take these two concepts, the geometric partition and the dynamical quantities, and we're going to make a little bit of room for something else called symmetry. And the dynamical symmetry is at the heart of these two concepts. When we talk about conservation of momentum, we're talking about a system in which there's a spatial symmetry. And when I say that, I mean that, for instance, in terms of boxcars, if you move the boxcars left or right, forward or back on the tracks, there's no different set of forces. Okay, so the equations of motion do not change under a spatial shift. And as a result, we get conservation of momentum. Same thing with a temporal shift. If your equations of motion do not admit some kind of fundamental change, if you move forward a microsecond or backwards a microsecond in time, which is harder to visualize, but the equations of motion, if you do have them, will show problems if you try it, and if you do have problems with it, if it does change, then you don't have conservation of energy. But if there's no change, the equations do not change under a temporal shift, then you have something called conservation of energy, which is really important. And these two conservation laws are related to these two spatial symmetries. Now, not all systems have conservation of energy or conservation of momentum. But when there are symmetries present, there's always some conserved quantity. And we'll actually talk about another conserved quantity called angular momentum probably Thursday. And oh, by the way, I'm writing a new chapter for my textbook, and being as how I'd like to be generous in all my actions, as generous as I can, I'm going to, when I finish writing the chapter, I'm going to give it to you guys as a free PDF. So don't all start clapping at once. I don't. I'm just kidding. I know you're not thrilled by it. But anyways, I'll give you guys, I'm writing on a new chapter on angular momentum. It's going to be pretty cool, and I'll give it to you for free when it's ready. Oh, and by the way, there is a student in here who I will not name who asked me, Dr. B, I have a percentage on the grades in the, I don't know, the upper right of your grades page, or the upper right of your, what do they call that thing? The first page in web courses, what do they call that? The home page, I guess. And it's got a little tab up at the top for grades, and it's going to read 72% or and then on the grades page in this course, you click on grades down at the bottom. It's got a bunch of and what I've said to many students over the semester is pay no attention. Have I got your attention now? Pay no attention to those percentages. They're completely wrong. They have nothing to do with our syllabus, and our syllabus spells out the grading procedure. So if you see a 78 or a 98% for my class, now your other classes, they may actually use them. But in my class, no way, Jose. All right? So now, and also as a side note, I have about approximately 1.4 metric tons of clicking data to upload, all the way back to lecture 8. So I'm exactly half a course behind. Half the course is up, half the course is not up yet. So I got a lot of stuff to update. But the web courses, they don't care about that. They just willy-nilly do all these percentages, and they don't know anything about my syllabus. I can't program my syllabus in, unfortunately. I wish I could, but it's just one of those things about Canvas that it's it's not ready for prime time, but here we are in prime time using it. Anyway, so this dynamical symmetry idea is something, it's of profound physical interest. And the woman who discovered this, her first name was Emma, and from Germany, and her last name was Noether, Noether. She was a refugee from Germany during the Hitler Zeit, during the time of the Nazis in Germany. She came to the United States and worked over here in Philadelphia at one of the colleges, I think Bryn Mawr College. Very smart physicist, and she came up with this theorem about symmetries and conservation laws called the Noether theorem. And Noether, Noether, Emma Noether. So fantastically important, and we'll talk about it some more when you get your free chapter on angular momentum. Now I want to talk about exchanging momenta and energies. Exchanging momenta and exchanging energies. Now with the skateboarders and stuff, the box cars, we talked about how they exchange momenta. They have interaction forces, and each one of them gets the same size chunk of delta P. The box cars that were at rest get a little bit of rightward delta P, and the box car that's flying in gets a little bit of leftward delta P. It slows down just a little bit, and they lock, and of course they lock and they move off together into the sunset. Skateboarders too, and you can calculate that. Matter of fact, that's in chapter 4. But what about energy exchanges? That's what we're going to talk about today. Delta E, we computed some delta E last time, and we're going to do some more delta E today. But this is our big question for the day. What about exchanging energies? Momenta, skateboarders, easy to see. Energy exchanges are everywhere, but they're harder to see. But let's work out some energy specs using the baseball. And what we're going to do, the basketball. So we're going to use this trajectory that we used last time, the 18 meter drop increments, and we're going to do one 18 meter drop. And so I see you guys, I can hear you getting your clickers out. And yes, we're going to click here, but let's lay out the strategy. First spec is that we have a 0.620 kilogram basketball. And the first thing we're going to do is figure out a weight force for it. And then we're going to figure out the work through one of the drop segments. Delta y equals negative 18 meters. And the negative sign means that it's going downward. So you could think of this symbol delta y as being a little vector. It's called a displacement vector. Then we're going to calculate the corresponding change in the kinetic energy for one of these segments. And then after that, we're going to think. We're going to think it over. And that's what my objective is. You can teach, go over there to the College of Engineering and round up a bunch of engineering majors, and they can memorize out the wazoo. But, so if they can do it, anybody can do it. But what we want to do is think, and think carefully. So but to think, you got to have some stuff to think with. All right, so let's get down some specs. What's the weight force on this basketball? This should be easy as walking through a park on a sunny day after eating pumpkin pie. Bye bye, Miss American Pie. Drove my Chevy to the levee, but the levee was dry. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Wow, 295 students just answered. But did you answer correctly? And apparently 96% of you. Good. So this is 96% of you got this right, and you did it pretty quickly. Good. That's the first spec that we need for today's stuff. All right, next one. For a falling basketball, is delta y parallel or anti-parallel? Anti-parallel means the opposite direction. Parallel means the same direction. All right, so go ahead and answer this one. Think carefully. And amend your notes to reflect the size. And put a minus sign on that weight force. Falling basketball. 15 seconds. 10 seconds. 5, 4, 3, 2, 1, 0. 295. Very good. All right, let's see what you guys answered here. Yep. Most of you got this one right, parallel. Hey, students, if you, 9% of you answered anti-parallel. But everybody ought to write down anti-parallel as a vocabulary term. Here's the definition. Two vectors are parallel if they point in the same direction. Two vectors are anti-parallel if they point in opposite directions. So two vectors are parallel if one of them is north and so is the other. They're anti-parallel if one of them is north and the other is south, for instance. Two vectors are parallel if one of them is northwest and the other is northwest as well. Two vectors are anti-parallel if one of them is northwest and the other is southeast, opposite direction. Okay, so good work on that, you guys. Now, next question. See, these are all the kind of things that you've got to do in order, let's say that you get tripped up on number 4 on the homework. And you don't want to go through life getting tripped up by problems like that, all right? So what you got to do is think your way through all these things. And that's why we're going through these specs and just kind of working our way through the different decisions that you have to make. Okay, next decision. Which formula do you use to compute work? I got a bunch of them here, and some of these are righteous. There's a good answer and there's a true answer. Some of them are spurious. Some of them are true equations, but only one of them is the proper answer to this question. I see a lot of people paging back and forth in your notes. 15 seconds. That's good. If you have notes, that's why you use them. Go back and look at them. 5, 4, 3, 2, 1, 0. 295. Very good, 91%. This is the work formula. And now if you want to jot down a couple notes about the work formula, here's what you want to remember. Shh, 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 shh. What you want to remember is the component of the force that's parallel to the path, F parallel, that's the one that changes speed. Okay? It'll either speed it up or slow it down. If you have some centripetal newtons, which you can have, they'll change the direction but not the speed. All right? Because centripetal newtons, by definition, are perpendicular to the path. Okay, so F parallel, and then delta y is an increment of the path, and you can think of that as being, parallel to the path as well. Okay, so if it's a free fall path, it's exactly parallel. If it's a curved path, it's delta x or delta s in general might not be perfectly perpendicular, or excuse me, it might not be perfectly parallel, but in the limit of very, very small delta s's, yes, you can consider it parallel. Now, question for you. So this is a nice little mini review. Equation A, righteous or dangerous? Righteous or dangerous? If it's righteous, identify it. If it's dangerous, tell me why it's no good. Raise your hand. Who can be bold? Fortune favors the bold. Equation A. Is it a righteous part of a formula? What do you think? Here in the front row. And what formula? We have a young lady in the very front row who says yes. What formula is it for? She said it's another version of like F equals ma. Hey, what's the general name in words of F equals ma? No. Newton's second law. Yeah. So, yeah, F equals ma, or Newton's second law. Good. So this is the ma of Newton's second law. Option B. No, not really. I mean, it's F centripetal times delta y is nebulous, it's dubious. So that one's in there to kind of confuse you a little bit, or if you're and actually, whoa, 2 people chose B. But look at what I've got as in my notation here for see, for B, no way. All right. Now, for C, you can see that my notation down here is that this is the centripetal the centripetal force formula. So that one is righteous. And then, of course, D is the correct answer. So 3 out of those 4 are righteous. Now, I want you to hit the refresh key on your on your iClicker. Because we're going to do a calculation now, and now we're ready to do the work. Hey, can I ask you a question? The work is negative 6.076. Delta y, is it positive or negative? It's negative because it's dropping. Okay, so negative times negative is, all right. So you're going to get a positive number for this calculation. Go ahead and start. And you'll need a minute or 2 to do this. But if you were trying to work on the homework, number 4, this is it. And I posted in discussions a thread of it. Do you remember seeing this in discussions? And I think Angelina, in discussions, gave some advice that I didn't really like very good. This is the formula to use. So type into the nearest tenth of a joule and then hit the send key. Nisha, why don't you come up here and take a look at this? See, this is how my display is. Now this is what the students see. Okay, and this is my next screen, so I can always see what's coming up. And then this is the clicking software. And right now there 22 students have answered. This is how much time they've taken. And this is the question number. Work on the basketball. Okay, so and this is a calculation question. And on exams, we have the students will do calculations. See, it's when when I was doing 2048 with Sri Ram, we had written exams, and so that's we did a ton of grading. But with this, I can do simple calculations, and I can still do partial credit because all their data is compiled into a spreadsheet, a CSV file, and so I can analyze it very quickly. And so you basically won't have much grading to do, but helping out and stuff, and coaching students, yeah, a lot of that. That'll be fun. Okay. All right. Huh? Yeah, in web courses. And sometimes if a student asks you in class too, that's good too. Like this young lady sitting next to you, or this one. Yeah. All right. All right. What are you reading? Aha, pattern recognition. Very nice. Good. This is great. I love seeing it. Students working on their calculations. Love it, love it, love it. Let me give you some light. Okay, 1 minute. Good, 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 good. You know what I need is a drone. I wish I had a drone so that I could fly my drone and see what you guys in the backs. I could see the first 4 or 5 rows pretty good, but the guys in the back, I can see what you guys are doing on Facebook or Reddit. All right, 20 seconds. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Zip zap. Come on, 295. Get you guys' answers in. You're really going to be straining your brain by the end of class today. I hate to say it, you guys. You're going to... 292. Come on, you guys. Hustle. There's 295 of yous. All right, you had a chance. 293. Okay, I'm stopping it right now. Five minutes. All right, let's see what you guys answer. What? 109.4 is correct. Very good. Very good. Some of you have negative 109.4. I don't know what this one is though. See, now you guys listen up carefully. if I was to ask you this question on an exam in the clicker part, I'd be I'd be able to look at all your answers in a spreadsheet and sort them out very carefully. And I'd see a bunch of people here with 109.4 negative, and I'd be able to say, ooh, they forgot a minus sign. So I might give them partial credit, 2 out of 3, okay, because they just dropped a minus sign. But somebody here, 31 of you typed in 1,071.8. I have no idea. 9.8 times 6.76. Oh. Yeah, so the what you want to do is basically just the product of the weight and the drop distance. Okay, so let's look at what we got. All right, first of all, here's our recap, our summary page. Negative 6.076 for the weight force. Negative meaning downward. Shh, 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 shh. The work is positive because it's negative times negative, so that's a positive. 109.4 joules, 109.4 Newton meters, 109.4 kilogram meters squared per second squared, to the nearest tenth of a joule anyways. Therefore, that is the corresponding change in the kinetic energy. Okay, so as soon as you know the work, that's the definition of work. The change in the kinetic energy from F parallel, basically. Now, thinking. Here's a question. Jot this down. Could you figure out the change in the speed from knowing the change in the kinetic energy? And I'll leave that as an open question to be solved tonight on homework. Question in the back. Free fall is no. I know what you're thinking. The student asked me. I thought that free fall was positive gravity. Little g, is written down as a positive number in the front or back of a textbook, 9.8 meters per second squared. Physically, it's always a downward acceleration. Now, a lot of times you can do a simple thing like just if you're dropping something from the top of the library, just use 1/2 9.8 times the square of the time. But if you're trying to track positions carefully, as we are, or displacements and forces, then you have to use minus signs, so negative 9.8 meters per second squared, judiciously and correctly in order to adequately express the downwardness of it. And then positives will be upward. All right, so it's in the case of work, there's a difference between doing negative work and positive work. If this thing were and students, I see your hand, so I'll get to you in just a second. If you were to do positive work on the way down, that means that on the way up the same 18 meters, and that's what a baseball does, it loses speed on the way up, right? Okay, so that would be delta y positive, but weight force still negative, anti-parallel, positive times negative, and so the quantity, that product is negative. Okay, so, and that's what baseballs do. They lose kinetic energy on the way up. Okay, all the way to the back. Question. 104.9. Ooh, that is a typo. I'm not going to try to mess it up now. That should be 109.4. That's dyslexia on Dr. B. My keyboard is dyslexic, I guess. No, is that what you guys were asking about over here? Okay. Yeah, it's supposed to be 109.4. Sorry about that. So here's a, Tanisha, I'll get you in a second. Here's a question. Could you figure out the change in the speed? I'm going to give you some homework tonight, hopefully by supper time, if not sooner, in which you're going to grapple with that question. In other words, if I tell you that you have an increase of 2.5 joules of kinetic energy, can you figure out the change in the increase in the speed? And it's not a simple problem, but it's not that hard. So you're going to be working with that. Tanisha. The question is, will the work always be the same as the change in the kinetic energy? And the answer to that is yes. That's the definition of work. Work is defined as the change in the kinetic energy, delta KE. And the way that you compute it, the formula for computing it, Tanisha, is F parallel times delta Y, or F parallel times delta X if you're going horizontally. Okay. Any other questions? Okay. Now, question 4B. The basketball gains kinetic energy. So does something else lose kinetic energy? The basketball gains, the skateboarders gain leftward or rightward momentum, but what about, does something else lose kinetic energy? Hit your refresh key. And now I want to probe your brain by asking you a question. Here it is. What loses energy as the basketball gains kinetic energy? Talk it over for a minute with your neighbor. Decide on an answer and then type. And just type, no codes, just type in a straight word or two. Like, what loses energy? Chuck Norris. Not. So obviously what loses energy? I have one answer. Go ahead and start. We're not going to have a Geneva conference about it, so just take a minute to talk and start clicking in an answer. And don't click in, okay, we got 7 answers now. Don't type in a poem. Don't even type in a haiku. You couldn't really get a haiku with this 14 characters anyway. I hear clicking. Clicking, clicking, clicking. Hopefully this will help you see your clicks. Miss Romero. TJ. TJ. Getting your answer clicked in? Huh? Good. All right. I don't like hearing that cough. That doesn't look very good. You know what you should do is you should take some ginger. Make some ginger tea. Yeah, that's really good. But don't use Chinese ginger. Only like Guatemala or USA. What? Can you what? Yeah, you can get it at Walmart, but sometimes they sell Chinese ginger. And I never eat food from China if I can help it. Huh? Take it, yeah, take it some in the morning, and it's really good for any kind of inflammation, and it's good for your stomach. Ginger's really good for everything. I don't know if it's good for for exams, but it's good for recovering from exams. You know, when your brain is totally inflamed. Yeah. All right, 1 minute. Office hours tomorrow, 9 a.m. to noon. Dr. B's building, physical science. Be there or be a rectangle of equal sides. 15 seconds. Physical science building, PSB, room 158. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, 291 responses. Oh, now this is cheating. I'm going to go down the list. There's a bunch of... All right, let's look at some of these. The most frequent answers were correct answers, but that's because it's people that have already had a physics class or something. Gravity. Gravity. Does gravity lose... Shh. Does gravity lose energy? I don't know. It depends on what you call the gravitational system. So if you call the gravitational system one Earth and one basketball, then the basketball's got more kinetic energy, and the Earth's going to have a little bit of extra kinetic energy. So let's look at some more of these remarks. Basketball. The basketball doesn't lose energy as it... Okay, kind of maybe, I guess. The basketball. Weight force. This one is definitely wrong. Why is... Shh. You guys are talking a little bit too much today. Why is weight force incorrect? Why is it wrong to say that the weight force loses energy? Why would you say in the back? Weight force is not something that can gain or lose anything. It's a force, okay? An object can experience a force, an object can have kinetic energy, but a weight force, and in fact this force is a constant. So that one's out totally. All right, hit your refresh key again. Just when you thought it was safe. Just when you thought it was safe, we're going to talk about water balloons. All right? Now, I want you to go ahead and write down the text of this question. Multiple choice. You're seated 5 meters up in a tree with a 0.400 kilogram water balloon. Just like Calvin and Hobbes here. And the balloon is at rest, but it's ready to drop on anybody. What is its kinetic energy? 30 seconds. Think, think, think. Read carefully and think. 15 seconds. Five, four, three, two, one, zero. Students, let me ask you a question. Let me ask you a question. The, the balloon is at rest. So it's got to be this. All right. Now, if you were thinking about something else, this is one of those questions where I tell. Did you guys write it down in your notes? Next question. You're seated 5 meters up in a tree with a 0.400 kilogram water balloon. It is at rest but ready to drop on anybody. How much work will gravity do to it on the way back to the ground? And oh, by the way, the question where you typed in your own answer, a word or two words, everybody's going to get that correct. That's more like a survey question, so everybody gets a free point on that one. But this one you got to do it carefully. How much work will gravity do it on the way back down the ground? So in other words, just before impact, a full 5 meters drop. Thirty seconds. Ten, nine, 8, 7, 6, 5, 4, 3, 2, 1. Wow, 297 answers. Good. Looks like we got a little bit of splaining to do here. 3.92 newtons is wrong. The correct answer is 19.6. And the majority of you got it. Now, what is 3.92? I don't. 0.4 times 9.8? All right. Okay, so if you typed in 3.92, oh, that's the weight force. Okay. Yeah, so if you typed in 3.92 newtons, you were thinking about the weight force. But no, the work that gravity does is weight force times h, 5 meters. So that works out to 19.6. Easy way to do this, mgh. Hey, you guys, write down. Shh, 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 shh. Still talking. Yep, still talking. Doesn't even know that I'm looking at her. Yeah, it was you I was looking at. You're still talking. Come on. You're distracting the people around you as well. People sitting in the back, they complain all the time. You guys in the back of the room think you can talk because I can hear all this stuff. I just can't make out what you're saying, but I can hear that you're talking. The acoustics in here being what they are. Now that's also the case that it's going to distract somebody behind you that's working their ass off to, excuse me, that's working their you know what off to get a good grade or even a decent grade. Okay, so don't distract other students. All right. Now, the way that I would tackle this, it's MGH. MGH. So, and then work with your minus signs if necessary. This is just asking for a number, so 19.6 is good. 5 times 0.4 is 2. And 2 times 9.8 is 19.6. So that's the way I would do that one. You could do it in your coconut. Now, let's keep going with the lecture, with the topics. What we're talking about, and actually this was the top 2 answers for the type in your own answer question. Potential energy. Students that already knew the secret answer that I was driving you toward answered potential energy. What we've been talking about for the past few minutes is potential energy, which is an enormous tool. It is in the theory of relativity, when we talk about the curvature of space-time, and Einstein's famous equation E equals mc squared. When we're talking about the curvature of space-time, like by a black hole or something, we talk a lot about potential energy. So, and all scientists do. All right, so generic energy formula for GPE, gravitational potential energy, is mg delta y. Now, in this particular case, use 9.8. And that way, when delta y is negative, it'll signify that you're losing potential energy. But when delta y is positive and increasing altitude, you'll be increasing your potential energy. And so, and of course, decreases when it's negative and losing altitude. So this is the thing that this quantity, potential energy, is the thing that we think of as being exchanged. So kinetic energy and potential energy are always in a state of exchange if something's in motion and accelerating. Okay, so if it's accelerating, you're either translating potential energy into more kinetic energy or into less kinetic energy. So for every kilogram of mass of the object and for every meter of altitude of the object, the GPE is defined, and for this reason, we call the potential energy the energy of position. And there's an enormous amount of calculus behind that, which we won't go into, but this is one of the reasons why we call potential energy a very fruitful and productive concept. All right, and so one way you can think of it is an exchange. The basketball. If it's like if you have a banking account and you swap some money over to your savings from your paycheck goes into your checking account, and then from there you transfer some over to your savings. And so you still have the same amount of money on the books, but one is missing $200 and the other one's got more, $200 up. So it's a lot like that. For something in free fall, if it's on the way down, it's gaining kinetic energy. For every gain of a joule, it's lost a joule of potential energy. All right. So now let's talk about, just for a moment, the space shuttle. Now, this is a great photo. A few years ago, I believe this was Atlantis. altitude 160,000 feet. So it's way up there at the edge of space. And it's traveling Mach 9.1. This is an infrared photo. And this is for this is relative to an airborne, it's basically a big 747 or a 707 with a big dome on it with a big infrared, monstrous infrared telescope. So basically when they do pictures like this, they're basically telling the Russians, yeah, we can see every single thing you got in orbit because we can see this. You can see this space shuttle from our airplanes. So now 9.1 is about 7,000 miles per hour. Go ahead and write that down. 160,900 feet is about 50 kilometers of altitude. 28.2 nautical miles. Yeah, so this thing is so what we're going to do is work out a reentry problem here for the space shuttle. And from 50 kilometers all the way down to Kennedy Space Center, y equals 0. So now here's a picture. This is basically the reentry attitude. Straight down the dotted red line is toward the center of the Earth. And so the space shuttle's it goes, to brake. And this basically is how it's kind of like when you're driving down the turnpike, you have your hand like this horizontal, your hand slices through the air, but when you turn your hand into the wind, it really pushes your hand back. And same thing with the shuttle. You get a lot of aerodynamic drag in this attitude. Now the mass of the STS, the space shuttle, is about 100 metric tons. Okay, and we're going to work with that. The landing speed needs to be 215 miles an hour. That's pretty fast for a regular aircraft. I think regular aircraft land at about 100 miles an hour. But of course, the space shuttle has a really long runway, and it also has big parachutes, speed chutes at the back. Okay, now what we're going to do is call that 100 meters per second for a round number. All right, so 100 meters per second will be a little bit bigger than 215. So we'll just round it off to 100. All right, and we're just going to work it through. Okay. Now, from this altitude, let's say that it takes 12 minutes, and that is a realistic time. From 160,000 feet, 50 kilometers, 12 minutes later, you're hitting the pavement at Kennedy. Okay, so that's about 720 seconds. And so just think about how much energy is dissipated in 720 seconds. And then you'll know why the space shuttle, even when it lands, it shows up on infrared night vision camera like a torch because it's so hot. It's designed to hold that heat and withstand that heat. So let's try to figure out how much energy is dissipated and how quickly it is dissipated. All right, so you've got the specs there in this outline, and we'll keep writing them down. So I'm going to go to the next slide, and here's the mass: 100,000 kilograms, 100 metric tons. That's the same as 100,000 kilograms. Now, 7,000 miles per hour is about 3130 meters per second. So there's my V1. Here's my delta Y. It's about 50 kilometers, 50,000 meters. So if there's no such thing as air resistance, it's going to gain a lot of joules of energy going down through 50,000 meters. I mean, even 1 meter. Oh, okay. No problem. Even 1 meter for the space shuttle. If the space shuttle dropped on your toe, you'd know it. So, because it's got a lot of energy. All right, so kinetic energy, 1/2 mv squared, mg delta y for the GPE. Total energy, and this is the thing that's conserved, really. The total energy is KE plus GPE. All right? And that has to be dissipated almost to zero by the time it lands. All right? Now there's somebody asleep in the aisle seat, one seat, one row from the back. So we got various braking methods. You know, they do big, huge S-turns. In other words, these guys in the space shuttle, it's incredible what they do. They start doing S-turns over the Indian Ocean, and by the time they're at the end of their first turn, they're over the South Pacific, and then the second S-turn, they're over California. It's unbelievable what these planes can do. All right? And basically what they're doing is trading altitude for kinetic energy, and try to dissipate a lot of heat energy. All right? So that a lot of the heat goes into the atmosphere. They're heating up the atmosphere. Okay? It blazes this trail through the atmosphere. But the space shuttle gets hot too, so that's why it's so hard to work with. You know, so dangerous. All right, so let's do this. Kinetic energy 1. All right, here's the calculation. 0.5 times 100,000, 1/2 mv squared. And hey, you guys, 3130 meters per second quantity squared is 9,796,900. You can verify me on your calculator if you want, if you got your calculator out. 3130 quantity squared. And notice here in the middle that I have the quantity meters squared per second squared. Don't forget that. Right? And that's going to give me a joule, because look, I've got a kilogram here in the second parentheses, and I've got meters squared per second squared in the third parentheses. So you put those together, and that's a joule. All right? And you're going to have to do scientific notation on this one. 489.8 times 10 to the 9 kilogram meters squared per second. And that is a lot of joules. All right? Now, that's up there at altitude. And so, when you're up there at that altitude, you've got basically 490,000 billion 10 to the 9 joules of kinetic energy. And then, all right, so go ahead and write it, 490 billion joules. And then you've also got a bunch of GPE that can be transformed into kinetic energy if you don't bleed it off into the atmosphere. So let's figure out mg delta y. Now, we've got negative times negative, so I'm not even going to write them in here. It's mass of 100,000 kilograms times good old 9.8 times 50,000 meters. All right, so that again is a big number of joules. When you calculate it out, it works out to 49 times 10 to the 9 joules. So I'm working this problem in billions of joules. Kinetic energy, 490. Potential energy, another 49. So you've got to get this basically pretty close to zero for landing. You know, you're only going at 215 miles an hour, 100 meters per second when you land. And you're landing at sea level if you're landing at Kennedy, so your potential energy is down to zero at that point. So here we go. Your total energy is 539 billion joules. And I'll just give you this figure at land. Kinetic energy on landing is 100 meters per second. 0.5. Go ahead and write down 0.5 billion joules. And that's basically this calculation here. All right. So you've got to bleed off 438.5 billion joules. You still want a little bit entering the runway. 500 million. And so you've got to bleed that off into the atmosphere and into the airframe. And we're not done. We're not. We got 5 minutes. What are you closing up for? No. It's on the video. It'll be on the video. So here's your energy dissipated. 538.5 times 10 to the 9 joules. That's a billion. 538.5 billion joules. And you've got to dissipate that in 720 seconds. Now, side concept, power. Delta E over delta T is known as the power or the dissipation rate. Okay? And it's measured in joules per second. And that has a fancy word. In this particular case, dissipating almost all your kinetic energy and potential, 538.5, and leaving 500 million for the runway, which you're going to, dissipate that with the parachutes and brakes and stuff. Okay, dissipate that in 720 seconds. That means that you have to dissipate 0.748 billion joules every second on the way down, on average. Now, the fancy name for that is billion watts. A joule per second is also known as a watt. A watt second is known as a joule. So this is 0.748 billion watts of power dissipated on average by the space shuttle on reentry. And another word for that is a gigawatt or a gigawatt. 0.748 gigawatts. And the biggest power stations in the United States put out maybe 10 gigawatts of power. So this is quite a bit. And make a note of this side concept up here. The rate of production, use, or dissipation of energy is called the power, and it's measured in watts. And this is the biggest dam in the United States, Grand Coulee. And it puts out, it's 550 feet tall. It puts out 6.809 gigawatts of power when it's completely open. Okay, homework 12 will be running hopefully by supper time tonight, if not sooner. You're dismissed. I'll see you on Thursday.